All right, we are recording. It is 11 o'clock, so it's time to get started. Wonderful to see everyone here today. Welcome. This is a very special Womanium Quantum event. Maybe I'll kick off by telling you more about Womanium. So Womanium, we started in 2017, and the goal of the foundation is to advance science. And we asked ourselves, how do we advance science? And one way, of course, is to bring more people and more young minds into the scientific field. And this is where we started Womanium, to bring more minds, especially more female minds, into the scientific world. So this is a bit of the origination of Womanium. And thank you all for being here today. Raj, over to you.
Hello, everyone. Welcome to the Womanium program. Womanium was created in 2017 with the goal of creating the next generation of female scientific leaders. But our programs are open to both men and women. And we do it by taking the best students and introducing them to the best minds who are doing the best scientific work in the world. And we have felt that there is a lot of times when there is a mismatch between the people who are doing cutting edge scientific research, innovation, etc., and the young people who want to become that. They do not get to see each other and learn about each other's work. And therefore, the passage of knowledge gets delayed. So we take young people and expose them to the cutting edge of scientific work that are done by leading research labs in the US, as well as companies, industries, etc., and also companies from other countries. In that capacity, we are the only foundation to have worked with DARPA on many of their programs. We are the only foundation to have worked with ARPA-E on 35 of their programs in energy. We are the only foundation to have worked with the National Institutes of Health to create one of the largest computational neuroscience programs in the world, for which we were even given an award by the directors of NIH. We are the only foundation to have worked on James Webb Space Telescope's testing. And then, 1 second. I got an instruction to turn off my Discord. So we are the only foundation to have worked with NASA on the James Webb testing, as well as Hubble Space Telescope. Then we have always tried to create the next generation of programs by looking at what is happening at the leading edge of industry, science, and technology. And we realized that one of the new and emerging fields that is fascinating, but also needs to be introduced to the next generation of thinkers is quantum science, specifically some of the domains of quantum computation, quantum sensing, etc. And with that in mind, we decided to create this program that first looks at the quantum computational aspect of it. And that is why we created this program. And this program will be followed by another program that will look at quantum sensing, quantum metrology, etc. And therefore, we are really glad and happy to have a very young, curious, determined, intelligent scientist here today named Bill Phillips. During the previous discussions with him, I was really impressed by his childlike curiosity, his eagerness to engage with the world, and also his playfulness. Bill, of all the things that I liked about you during your previous discussions, one of the things that I like about you is that your eternal youthfulness. Speaking of eternal youthfulness, Womanium is currently working with the National Institutes of Health and the National Institute of Aging to create a program on the biology of aging. Perhaps you will be an interesting person that we should actually study. But jokes apart, science has to be made fun. And thank you for coming here and sharing the excitement of science with us. And let me introduce another young scientist who also shares that enthusiasm and curiosity, and who is also at NIST, Dr. Marlu Slot. She's a quantum material scientist at NIST. And I will let Marlu introduce William Phillips. Over to Marlu.
Thank you, Raj. In the same building at NIST as William D. Phillips, a building of atomic clocks that are defining the time standards of today and tomorrow, quantum simulators unraveling novel physics, quantum computers that will solve problems that we cannot solve with the computers available now based on atoms. And the secret for all of these are controlling atoms, getting hold of them. And that is a true challenge, because imagine a gas of atoms, they move with 300 meters a second. How to control those? Our guest today, Bill Phillips, was able to slow them down and bring them to a standstill using lasers. Laser light exerting tiny forces on those tiny particles, the building blocks of matter, atoms, large enough to slow them down, bring them to a standstill, first at 100 millikelvin, almost absolute zero. This was not enough for the group of Bill Phillips. They slowed it down further to about 40 microkelvin. And this was incredible because it was not only incredibly low, it shattered the theoretically predicted limit at the time. And eventually they got more than 200 times lower than what was thought theoretically possible. In the meantime, another breakthrough discovery was done by Bill Phillips and his team. They saw that the atoms being cooled down and trapped with those laser beams weren't positioned randomly. No, they were neatly arranged in a pattern defined by those interfering laser beams. And that was the basis of optical lattices that are extremely important, defining atomic physics now and all developments in next generation atomic clocks, in quantum simulators, and the next generation quantum computers based on neutral atoms. Our guest today is the man who worked with lasers, played with atoms, and the man who usually asks many questions, but today he is here to tell his stories and answer our and your questions.
It's a pleasure to be with you.
Thank you, Will. As Malu mentioned, your work on atoms has been fascinating. So tell us more. Raj also mentioned your childlike curiosity. So how did you play as a child that led you to play with atoms and light and lasers later on in life?
Well, I don't think my childhood was particularly unusual. I did all the kinds of things that most children do. I played games with the other children in the neighborhood. We would play kickball and baseball, and sometimes I walked alone in the woods and picked huckleberries and tea berries and ate them. Sometimes I climbed trees that I probably shouldn't have been climbing, but didn't break anything growing up. But perhaps the thing that was a little different was I had a laboratory in the basement of my home. Even when I was maybe 5 or 6 years old, I remember gathering together the kinds of things you find around in the house, salt and sugar and milk and orange juice. And I would mix them together to see what would happen, or I would look at them under a microscope, which my parents had given to me as a toy. And then as time went on, my parents were supportive of my curiosity about these things and got me proper chemistry sets so that I could have a wider variety of chemicals that I could experiment with. And like so many of my friends in that era, we would make rockets and shoot them off. And so those kinds of things, I think, helped to cement my interest in scientific things. And that along with a lot of the books that I read. I remember one of the things that had a big impact on me was a biography of Marie Curie. I just thought that her career was so amazingly exciting and even romantic. I mean, the idea that she died because of her commitment to her science. I mean, to a little boy, this sounds like a really romantic ideal. Not such a wonderful thing, of course, but we didn't understand about radiation poisoning back in those days, and she paid the price, as did many other people. But it seemed like an incredibly romantic idea when I was very young.
Yes, indeed. Even Marie Curie was one of the inspiration for us to start the foundation, along with an interesting story of another scientist called Ethel Brown Harvey. And interestingly, Ethel Brown Harvey, she discovered some of the biology of parthenogenesis, where two daughter cells come and create another daughter cell, two cells come and create another daughter cell. And she died in 1955. And in 1957, all the people who worked under her, they won the Nobel Prize. So many people do not know her because of that. But the National Academies has got an 8-page biography about her on their website. So you mentioned about some of the interesting things that you did in childhood and how you were always a curious boy. How did that play out in the laboratory when you were conducting experiments? How did that inspire your playfulness, creativity, and experimentation?
Well, one of the things that I think has characterized the style of research in the research group that I've been part of for over 40 years at NIST is that our approach has been driven by curiosity. That is, we would often do things like go into the laboratory and say, I wonder what would happen if we did this, instead of sitting in our office and doing a careful calculation about what we would like to have happen, and then going into the laboratory and seeing that. We would take sort of the opposite approach. Both are very useful, I think, but our approach was often, let's just see what happens. Let's fool around and see what happens. One time I was invited to give a talk at a military laboratory by the research director of the military laboratory. And she said the main reason she wanted me to come was to convey the idea that just fooling around is a good way to do science. And I think it is. It's been extremely fruitful for our group. As I said, it's not the only way to go, but it's been really fruitful for our group, and I think it reflects the kind of curiosity that we share about the way things work.
Well, I think that the lady from the military was correct that fooling around is a fun way to do science, because many people take science so seriously that they fail to experiment because they're afraid to fail. And I think some of the greatest scientists are some of the biggest fooling around people.
Indeed. Earlier in my career, there was a period of time when people were arguing against what they called curiosity-driven research. And I think it was a really misguided point of view, because curiosity-driven research, in my analysis of the history of science, and I'm not a historian, is the way that real progress has been made. That people were curious about things, and that motivated them to look into new directions, and that's how we've really changed things in science. And so, any kind of an approach to science that thinks that curiosity-driven research, as opposed to, say, goal-oriented research, which is also important, but that somehow you should downplay curiosity-driven research, I think that's a really bad way of doing it, and it's going to have the effect of not giving you the goal orientation that you want.
Then when you had those ideas, curiosity driven, did you ever expect the impact that they turned out to have?
No, but I don't think anybody ever does. I don't think anybody can imagine the kinds of things that the things we do today, the kinds of impacts they will have some 10 years from now. People, when anybody says, oh, what's your long range plan? Well, I don't have a long range plan because I can't imagine what things are going to be like 10 years from now, maybe 1 or 2 years from now. But if I could imagine the things that I would be doing 10 years from now, I'm probably not doing the right things.
That's a good point. So you had told us that, growing up, you may have been a tennis player or a physicist. So tell us, what led you to become a physicist?
Well, okay. The idea of being a tennis player, when I was young in junior high school, what people call middle school today, and high school, I played a lot of tennis. And my friends and I who played tennis together sort of joked about, wouldn't it be great to become a tennis bum? Now, a tennis bum is somebody who's just barely good enough to make a living going to clubs where people play tennis and helping people learn how to play tennis, but not good enough to actually make a proper living. But, when you're a teenager, maybe being a tennis bum sounds like a good idea, but I was never good enough. I was just barely good enough at tennis to play on the tennis team. I remember that when I was in high school, there were 5 people would travel with the team and play the best 5 people on the opposing team. I was always 5th. When I was in college, 6 people would travel with the team and play against the top 6 people. I was always 6th. So,
guys, we really have to thank the tennis team for not admitting Bill.
Yeah, so that was never going to give me a career in tennis.
We are very happy about that. And how did you then get involved with the science that eventually led to your work at NIST?
Well, so that's, I mean, so many things happened. It's hard to know what really is the right story to tell. When I was an undergraduate at a small liberal arts college in the middle of Pennsylvania, I spent some time with one of the professors there. There's only like 2 people who made up the faculty of the physics department. And one of them was doing some work in magnetic resonance. And I joined him and learned a little bit about the equipment. And then I spent a semester at Argonne National Laboratory working with people who were doing magnetic resonance. So it all sort of came together. When I applied to graduate school, which, by the way, a little side story. I'm easily distracted. That's one of the problems with me, but sometimes it's a good thing. During the time I was an undergraduate, we got a visit from somebody, as we often did, who gave a colloquium and then also talked with the students about careers and such like that. So he spent some time talking with a number of physics majors about possible career paths. And I said, well, I've been reading about the rankings of physics departments. Now, this is before you could just look it up on the web. I mean, there was no web there. There were no personal computers at this time either. A computer that was about as powerful as my watch would take up this entire room. So it was a very different era for information. But I said, I've been reading these studies about, and I'd heard that Princeton was the top ranked place, and he had come from Princeton. And he said, a student from your college can't get into Princeton. I said, oh. So when I applied to Princeton. I applied to MIT, Caltech, Harvard, and I got into all of them. Probably because of the fact that I had spent time at this national laboratory and could get letters of recommendation from people who were actually known in the scientific field, as opposed to, people in my undergraduate institution. Well, I got a letter, on paper, written with ink and sent in an envelope with a stamp from the man who became my thesis advisor, Dan Kleppner at MIT. And he said, I was reading your application. I see that you've been doing some work in magnetic resonance. We're doing some work in magnetic resonance that's very different, but I think you might be interested in the kinds of things that you and the kinds of things that we're doing here with your background. Well, I visited Princeton, decided that it was nothing like what I wanted as a place to go to graduate school. And I called him from the lobby of the physics building at Princeton and said I wanted to visit. And I went and visited there, and I was just charmed by the dynamics of his research group, the way that the students interacted with him and with other professors. I thought, this is the kind of place that I really think is the right place for me. And I've never regretted that choice. I think that I was so lucky to have chosen to work in Dan Kleppner's group. He was such a wonderful thesis advisor, and the other students were just wonderful colleagues and mentors for me. And so how did things develop? Well, so I worked on a magnetic resonance experiment. In fact, I did a measurement that today is still the best measurement of that physical quantity 50 years later. And it's actually a little bit scary because people are using it to analyze these G-2 of the muon. experiments. And this is one of the things that goes into that. I'm thinking, nobody's done this again in 50 years. What if we made a mistake? Well, anyway, but what happened was about midway through my graduate career, we started to get commercially available tunable lasers. And this was a huge technological advance. It meant that you didn't have to be a laser expert to use lasers in the laboratory to do interesting things. And I was not working in the labs where they were using lasers, but I went to Dan and I said, look, I see these lasers. This looks like the wave of the future. I'd like to do an experiment involving lasers. And he says, well, we can arrange that. So we got together, talked about what might work. I did an experiment, which at the time was probably cutting edge, but in retrospect was really quite mundane. But what it did was it got me into this business of using lasers to do atomic physics. And then when I read a paper when I was a postdoc at MIT, I read a couple of papers about laser cooling. One of them was an idea that a guy named Art Ashkin, who did a lot of the early work on laser cooling, but got a Nobel Prize many years later for optical tweezers, which he'd done even earlier. And another one by Dave Wineland, who did the very first experiment in laser cooling trapped ions. I was interested in laser cooling neutral atoms. I read these two papers and I thought, there's really something here. I've got the background, the knowledge to do the kinds of things that are being talked about in these papers. I've got the equipment right here at MIT. Let's see what happens. So I just went in the lab and started to fool around and realized, this is harder than what these papers make it sound like it's going to be, or at least what Ashkin's paper, this idea paper, it was a lot harder than what his paper made out to be. But nevertheless, the core of the idea was so good and so exciting that in a certain sense, I could say I spent the next 10 years trying to do what Ashkin had proposed. And that 10 years established many of the tools that are still used today to do laser cooling in our group and in groups all around the world. So I don't know, I guess it was a kind of series of happy coincidences that led me along this path. Oh, another important coincidence is this. After I finished my degree at MIT in 1976, I did what they say you're never supposed to do. I stayed on in the same place for a postdoc. But I was doing rather different things. One of the things I was doing was working on Bose-Einstein condensation, which didn't achieve success for another 20 years at MIT, but that did achieve success using laser cooling in other places, not in my laboratory, or at least not right away. But anyway, so I did some other experiments in atomic physics, and then I applied to a number of places for permanent jobs. And I got an offer from a university, and I got an offer from NIST. And the offer at the university was clearly based on my experiences using lasers, and I probably would have continued doing things like studying collisions of laser-excited atoms and things like that. The NIST job was based on my earlier work on magnetic resonance and precision measurement. But for a number of reasons that were just lucky, I decided to go to NIST. And they said, well, since you've done all this atomic physics work, why don't you fool around with that a little bit while you're doing the other stuff, just to see if anything comes of it. And my thinking was, well, if I'm going to fool around with atomic physics, I should probably fool around with something that is related to what NIST is interested in. Well, what is NIST interested in that I can help with atomic physics? Well, atomic clocks. And I thought, well, atomic clocks, they're going to be a whole lot better if we can make the atoms go slower. So this idea that I'd been fooling around with at MIT that really didn't lead to anything seemed like the right way to go because I was at NIST. And the only reason I was at NIST was because of something that was part of my bygone past. So everything was just really lucky for me. NIST was very happy with the results of the laser cooling. Today, and I'm very proud of this fact, almost every big industrialized country has atomic clocks that work with laser-cooled atoms. The the United States, the civilian and the military timekeeping for the United States has as its primary timekeeping devices laser-cooled atomic clocks that are based on the kinds of things that our group had developed some years earlier. So that's really cool. The people who are building the clocks at the U.S. Naval Observatory, which keeps time for the military, were people who did postdocs in our group at NIST. So this is just really satisfying that this stuff that we did that started over 40 years ago has really borne fruit along the lines that we imagined. But even more exciting is that it bore fruit along lines we never thought of.
That is fantastic, Bill. At Womanium, we are proud to have worked with the US Naval Observatory on 57 of their atomic clocks. So hydrogen maser, rubidium fountain, and cesium. And we were very fortunate enough to take a lot of young people, especially young female students, to actually go and see the clocks. And it was a fantastic experience for them too. And they also got to play with the telescopes at the US Naval Observatory, which was again, an icing on top of it.
Now, there's all sorts of interesting things. As I said, I'm easily distracted. Hydrogen masers, you talk about hydrogen masers, really great clocks, especially for short term. My thesis advisor was one of the inventors of the hydrogen maser. So, the Naval Observatory, the original location of the Naval Observatory was a place where they kept time for the Navy. You have to know what time it is in order on board ship in order to navigate using celestial navigation. The whole idea of determining your longitude is based on timekeeping. And they had a ball at the old Naval Observatory that they would drop at a certain time, like at noon, so that people in ships getting ready to leave could synchronize their chronometers on board with this ball that was keeping, local time. And this is the origin of the ball that drops in Times Square at New Year's. It's not used anymore because, of course, we have other ways of navigating. We don't need to navigate using the stars anymore. We have the global positioning system, which uses atomic clocks. And but it's just an interesting piece of history.
Bill, do you have any other interesting pieces of history to share?
Well, probably, but they'll come up as we talk.
So we have an interesting question from Herman Colden, who's a friend of the program. He's originally done some work in the quantum field and now has a drone startup in Norway. And his question is, what do you think is the most unsolved problem in your field?
Well, okay, so there's so many ways that I could answer that. So let me answer it first in a really expansive way. So what I do is quantum mechanics. Okay, I often think of myself as a quantum mechanic, the person who actually does it. And that's what all of us in our experimental group are. We are quantum mechanics. We are working with this amazing theory born at the beginning of the 20th century that explains all about what goes on at the atomic and subatomic level, and amazingly, to some extent, that goes on at larger length scales, like in superconductors and superfluids. It is the most successful theory in physics that we have ever seen. It can predict the values of things like the magnetic moment of an electron to, I don't know, something like 12 or 13 significant digits. I mean, it's that good. And it is inconsistent with the theory that we now have to understand what happens on cosmological scales. Einstein's theory of gravity, which we call general relativity, explains what's going on cosmological scales. And all of the tests that have been done of general relativity are right on. Everything that Einstein has predicted has turned out to be true. So just like quantum mechanics, everything that quantum mechanics has predicted turns out to be true. In a certain sense, it's kind of boring. But I mean, there's another thread to that even though we understand all these things, we're surprised every day by the things that we learn in the laboratory. But here we have two of the most successful theories, two of the theories that defined in many ways the scientific tenor of the 20th century that are incompatible. That is, we don't know how to quantize gravity. It just doesn't make any sense. Something's got to change in one or both of those theories. So to me, that is the most expansive challenge that we face today, is how can we make quantum mechanics and general relativity consistent? And I have no idea. I mean, string theory is one of the things that people have been hoping would provide that. And so far, it's been a bit disappointing. But it might be that if we could find places where general relativity or quantum mechanics fails, that might give us a clue. You see, this is the let's fool around and see what happens approach. If we could find some way that general relativity fails, maybe that'll give us a clue as to where we should look. And what I'm hoping is that the incredible atomic clocks that are being made today by people like Anna Maria Ray and Jun Yi, my colleagues out in Boulder, might be one of the ways in which we find such discrepancies in what actually happens compared to what general relativity predicts. Looking at the edges, the extremes, is very often where you make progress, and the extremes of precision that can be had with these atomic clocks is one of the things that makes me excited about the possibilities of learning about these new directions. But there's other things like making an immortal qubit. Quantum information is one of the things that everybody's excited about these days. And one of the things we're going to have in if we have quantum computers as opposed to quantum simulators, things that actually crank out logical operations in a program, we're going to have to do error correction. And while we know in principle how to do it, and while we've demonstrated the process of error correction, no one has demonstrated error correction that is effective enough that it significantly extends the lifetime of a quantum bit, a qubit. These quantum bits, because they're connected to the environment, basically lose their quantum coherence, their quantum properties. And when they do, then the game is over in quantum computing. You've got to maintain that. And we know how to do it, theoretically, using error correction. And we know experimentally how to implement these things. It's just that the whole thing isn't good enough yet. And to me, that's one of the great challenges of our day, is to implement error correction that really extends the lifetime of qubits enough that we can do meaningful calculations with real gate-based quantum computers. But there's so many things that we're going to do before we get there that are really interesting. Short calculations, ones that don't involve very many gates, very many gate operations, and just do it quickly enough that the qubit doesn't decohere. But that's not going to get us everywhere we want to go.
And everything you mentioned are huge challenges, big projects. In 1997, you were awarded the Nobel Prize in physics together with Stephen Chu, Claude Cohen-Tanuji. Can you tell us more about the role of collaboration and competition in science for you?
Yeah, well, both I think have been very good features of my own career. So I remember I went to a meeting in 1983, the International Conference on Laser Spectroscopy, and I talked about the early experiments we were doing in slowing down atomic beams. This was so far from where we needed to be to do the kinds of experiments that we routinely do today, but it was a first step. And I remember talking with Steve Chu after my talk, and he gave a talk about some precision spectroscopy measurements. And he said to me, "Do you think there's anything in laser cooling. And I said, sure. I said, for one thing, nobody has trapped any neutral atoms. Well, 2 years later, he had trapped neutral atoms. Now, I'm not saying that he was motivated by that conversation, but it was probably one of the things that contributed to his interest in doing this kind of thing. And so having those kinds of connections, he and I continued to stay in touch with each other, very often calling each other up and saying, hey, let me tell you about the latest thing that we just did. And of course, we wanted to brag about what we were doing. And but at the same time, we wanted to make sure that the things we were doing were known to the scientific community and to the people who could make the best use of it. So of course we wanted to be first, but at the same time, we wanted to get the information out because we wanted to brag about what we were doing, but we also knew that the field was going to progress faster if more people were tuned in to what was happening on a day-to-day basis. And so the combination of communication and competition was really useful. I think it really propelled the field. Now, this conference that I was at, on my way back to the United States, I stopped in Paris, and I talked with Claude Cohen-Tanucci and his younger colleague, Jean Dalibard. Claude is about, I guess, almost 10 years older than I am. And no, more than 10 years older than I am. And Jean is about 10 years younger than I am. And we talked together about the kinds of things we were doing. And it was clear that the theoretical work that they were doing was really relevant to the kinds of things that we were doing. So it opened up a connection that has continued over the years. Jean Dalibard came to our laboratory and spent a few months with us. A few years later, he brought his family and spent a year in our laboratory. We did experiments and theoretical investigations together. I remember when we finally convinced ourselves that this observation that the temperature was way lower than what the theory had predicted was true. Because when we first saw it, we thought, well, obviously we're making some kind of mistake, because everybody believed this was a hard limit to how low the temperature could be. So we said, okay, we're making a mistake. We got to figure out what the mistake is. And after a few months, we realized, no, we're not making a mistake. This is new physics. This is something that nobody has understood before. So our first idea was, let's call up our friends in Paris and tell them what we've done and see if they can give us some insights. And it didn't take them very long before they came up with the key insights that explained what was going on, which then allowed us to improve things and get the temperatures even lower. And so that kind of connection was really important for the progress of the field, not just our own work, but I think the progress in the entire field of laser cooling, and later of Bose-Einstein condensation and quantum degenerate gases and quantum information processing and all the things that have come out of cold atoms.
So many fantastic insights and anecdotes and stories, Bill. And also one line that I noticed was that the field grows faster when more people are tuned in together. And that resonated because that is one of the objectives of Womanium also, to bring in more minds and to make them tuned in so that the field of science can grow faster.
Absolutely. In fact, one of the things that I think is really important that maybe I didn't emphasize as much is bringing people who bring to work on a problem, who bring different perspectives. So the more diversity you have in your team, to my way of thinking, the more likely you are to make progress, because people coming from different backgrounds, different mindsets are going to bring a different perspective to the problem. So I really think that, for example, our French colleagues brought a perspective that we never would have had, just because of the history of the way in which physics had developed at the École Normale Supérieure with people like Kessler and Roussel. There was a way of thinking about things that people like Cohen-Tanucci and Dalibard have continued, that really allowed them to attack this problem in ways that were very different from the ways in which we would attack the problem. Like Steve Chu was trying to work on the same problem. We had done these things and he thought, okay, what's going on? Well, he took a very different approach. And I think that the existence of those two different approaches was really healthy for the way the field developed. So I really like to have as diverse a team as possible.
That is wonderful to hear. We have listeners and participants from about 88 countries. So you mentioned about the differences in approaches, thinking, and tackling problems. Can you briefly elaborate a little bit more on that differences in approach and thinking?
Well, one of the things I often say, and it may be, as much a joke as it is a cogent observation, that the French approach to science is that they go into their office, they calculate what's going to happen in the laboratory, they go into the laboratory and they see exactly that happen. Whereas the American approach is you go into the lab and you fool around, and then you see something you don't understand, and then you go back and you call up your French colleagues and ask them to explain it to you. Or, whoever happens to be the people that you're connected with who have that theoretical understanding. Think about this. Now we're going back a long way in history. The 1920s, Satyendra Bose comes up with a new way of getting the Planck radiation law by creating what was, and I wonder, how did he come up with this idea? A different way of counting how many states photons could be in, by taking seriously the idea that they're indistinguishable. This was revolutionary. Nobody was thinking this way at all. He writes up the paper, it gets rejected. He sends it to Einstein. Who would have the temerity? A young physicist, he sends it to Einstein, thank heavens. Einstein looks at this and says, I'm sort of imagining here, oh, wow. He gets the paper translated into German and it gets published in a German. And then Einstein thinks, okay, what else can we do with this? What if it's not photons? What if it's atoms? And then he comes up with what we now call Bose-Einstein condensation. And, that kind of connection internationally at a time when it wasn't that easy to be connected internationally, right? The 1920s, we couldn't do what we're doing here. We're connected all over the world. And, Bose wrote Einstein a letter, and the idea, I don't even know if it was possible to call someone on the phone in 1920, probably not. I just don't know enough about the history of telegraphy and telephony. But he wrote Einstein a letter. And Einstein then wrote his own paper, sends it off to some of his friends, and the friends write back, people like Schrodinger, and the friends write back and say, no, you're counting wrong. And Einstein said, no, that's the whole point. This is a different way of counting that Bose came up with. And, how did he do that? Just pure genius, but the connections, why, a scientist coming up with this crazy idea in India, writes to a scientist in Germany who isn't doing that kind of work at all. And it just gels together into something which is now the basis of most of the new stuff that's going on in atomic physics. You can't make this stuff up.
True indeed. In fact, even in this call, you can see that there are you from NIST and the United States, And there is Dr. Marlu, who is originally from Netherlands, but at NIST. And there is Prachi, who is originally from many parts of the world, Hong Kong, India, and other places. And there is me from India, and all of us coming together with our participants from 88 countries. And I think the story that you mentioned is a fantastic inspiration for the world to work together on tackling many of the scientific challenges and problems. So Marlu and Prachi, more questions.
Oh, we have plenty. I really like the one from Nadine from the Utrecht, and she's a professor as well, previous colleague or friend of Marlu. And her question is, what are the scientific discoveries that happen in your lifetime that have changed your life on a day-to-day basis?
Oh, well, look, the invention of the laser. I was 12 years old when the laser was invented. And, that's been my whole career. Absent the laser, none of the stuff that I've been talking about happens. And then, you talk about connections. The laser exists because of the insight that Einstein had into stimulated emission. And interestingly, today, I'm still having discussions with some of my colleagues at NIST about the question of, do we really understand stimulated emission? We're still discussing it all these years after Einstein first proposed it as an important mechanism. So the laser is a huge thing, and so that's changed my life in a very direct way. Here's another thing that I don't think it hasn't changed my research, but it's changed the way I think about life in the universe. When I was a kid, there were no other planets besides the ones that orbit the sun. And now we believe that almost every star has planets. How much does that change things?
Yeah, and in fact, our foundation also had a program with the James Webb Space Telescope, where we trained students in testing the James Webb before it was shipped off. So yeah, now we know even more.
Yeah, the James Webb. I mean, what an amazing thing. I mean, that people really required not just skill, but courage.
Bill is hanging briefly, coming back soon.
It was done. All those steps worked.
Bill, your network is breaking briefly. There was some breaks. Yeah.
Okay, well, I'm not sure there's much I can do about yeah. See, I can see you're slowing down too. Choice of a number of networks, and I'm using the fastest one I've got, so I don't know what else I can do.
Yeah, it works again. Great. And there are more questions.
So I can stop my video, that might help, but I've never actually seen it help. But everybody says, oh, that's one of the things you could do is stop your video. But I've never actually seen it help.
Yeah, it's back. Great.
Oh, Bella, we like seeing you.
Yeah.
And there are more questions from our participants coming in. They are in the age range from 16 to all the way up. And one question is, for the younger and the older ones, what makes someone a successful scientist?
Yeah, that's a good question. I wish I knew. Okay, so when I give people advice, what should I do? What's your advice to me as a young scientist? The first thing I say is stay curious. I think that curiosity is the thing that distinguishes scientists from a lot of other people. Now, it's not that there isn't curiosity in a lot of other areas of life, but a scientist has to be curious. That's the thing that drives us. I mean, someone who is going to make advances has to be curious. And so you don't ever want to lose that. I think every child is born curious. And I think that what happens is that
Bill, you're breaking once again. Bill, 1 second.
Yeah. First, I don't know what to do. Let me kill my is that any better? Is my sound any better now that I've killed my video?
Yes, we can hear you.
Okay. Well, why don't I just complete this story and then I'll go back and turn the video back on.
Sounds great.
Great.
I think that every child is born curious. And for one reason or another, as we age, that curiosity is squeezed out of us. I think that in order to maintain some semblance of order, some control of chaos in elementary schools, we have to tamp down the natural inclinations of children just to run wild, which is part of what they're doing in indulging their curiosity. I think scientists are the children who resisted that, who maintained that high level of curiosity in spite of all the forces that tend to inhibit curiosity. In English, there's a proverb that says, curiosity killed the cat, that is supposed to tell us to rein in our curiosity, to not be so curious. But a scientist has to be curious. So I like to say curiosity killed Schrodinger's cat. I don't have any idea what that means, but but it's part of what killing Schrodinger's cat is part of our understanding of what quantum mechanics is all about. So that's perhaps one of the most important things, is to stay curious.
That is great. And the past 6 weeks, our participants have gone through a whole program about quantum computing. They learned about everything from the quantum basics to quantum hardware, quantum software applications. They are implementing them now themselves in a project. And one question from Victor from Mexico is, what is the application of quantum computing that you would like to see?
Yeah. I guess the main thing is what Feynman imagined in his famous 1982 talk and paper about which we all now think of as being one of the origins of the ideas of quantum computing, to do quantum mechanics. That there's so much in quantum mechanics that we cannot do, not because we don't understand the basic physics, but because we can't do the calculations. Because the difficulty of a problem, of certain kinds of problems, grows exponentially with the number of individual particles. Let's say we want to understand quantum magnetism, and we've got a whole bunch of interacting spins. The difficulty of solving that problem completely and with brute force increases exponentially. One of the things that annoys me is that people who aren't scientists often talk about something being exponentially hard. And then I ask, exponential in what variable? And they have no idea what I'm even asking. They just think exponential means really, really big. But exponential means that it's in the exponent, that the variable is in the exponent of a number. And that exponential growth makes it impossible for ordinary computers to solve certain kinds of problems. And today it seems clear that there are problems that require a brute force solution, or at least a solution that goes beyond the approximations where we turn a many-body problem into a single particle problem, like mean field approaches to quantum mechanics. It seems those won't work for certain kinds of problems. I want to solve those problems. I want to solve the Fermi-Hubbard problem. I want to know what the ground state of a Fermi-Hubbard Hamiltonian is for all levels of doping. Those kinds of things that we don't know because we can't solve the problem.
Makes a lot of sense. Next question, Malu, you're muted.
Then, of course, many people are curious about a Nobel Prize. How did it change your life? Is there a life before and after for you?
Okay, well, there's a number of ways in which the Nobel Prize changed my life. So one of the ways, which was certainly very positive, was I got more money to do my research. I had told my laboratory director on one or more occasions that if I had $1 million, now this was back when $1 million was real money, okay? That if I had $1 million, I wouldn't know what to do with it. And she came to me after the Nobel Prize and said, I would like you to reconsider your attitude about not knowing what to do with $1 million. Well, after I thought about it for a little while, I realized, yeah, there were things I could do. I could hire people who had just the right kinds of skills to come and join us at NIST. And that's how Carl Williams. I don't know if you know that name. Okay, so historically, a really big name at NIST, especially when it comes to quantum information. So he came to NIST because of the extra money that I got from the Nobel Prize. So that was a huge thing. I would say that Carl is probably the single person who's most responsible for the growth of quantum information science in the United States, the passage of the National Quantum Initiative, which is a huge thing. This was Carl, so that made a big difference. I mean, I brought him in. He did all these amazing things. So the ability to do that kind of thing, to say, hey, there's somebody who could make a difference and get them to work on the kinds of things that I was interested in. And of course, at that time, I wasn't thinking about quantum information, but it sort of came along, and he really focused on it in a way that really made a difference. So that was one thing. Another thing that isn't nearly as important, but a lot of people don't think of. People often say, oh, you have got a Nobel Prize, so you're famous. No, I'm not famous at all. If you were to go outside on the street of any city or town in the United States and ask 1,000 people, who is Bill Phillips? None of them would recognize that name as being somebody who'd gotten a Nobel Prize in physics. One or two might recognize the name as being somebody who's a bodybuilder and has written a number of books about physical fitness and things like that. So I'm not famous in the usual sense, right? On the other hand, having a Nobel Prize has meant that I have met people who actually are famous. So I once had dinner on New Year's Eve, sitting next to the President of the United States. Now, that never would have happened, no matter how much success I had as a scientist without the Nobel Prize. The Nobel Prize is something different. And so that's something totally unexpected that happened as a result of the Nobel Prize.
And we know that you get many invitations to speak. So it is really wonderful that you are here to speak with us.
And also, Bill, speaking of Nobel Prize and all the opportunities it has opened up for you, it reminds me of an anecdote by another Nobel Prize winner, James Rothman. When he received the Nobel Prize, he called up his mother and said that, Mom, I won the Nobel Prize. And his mother said, son, I heard that you can win too. So that is my statement to you too, Bill. You can win too.
Well, my mother, I think it might have been the thing that finally convinced her that it wasn't a good idea for my career to become a real doctor. She always thought I should have been a real doctor, by which she meant a medical doctor. A PhD really didn't cut it for her. That was not what she wanted for her son.
So she finally approves.
I think she finally thought, well, maybe this PhD thing isn't so bad.
About the legacy of neutral atoms being laser cooled and trapped, Nasser Belaloui from Algeria asks, of all the various applications of neutral atoms, which ones do you think will have the most impact in the near future?
Yeah, well, in a certain sense, it's easy to answer that question because neutral atoms as atomic clocks have already had an impact. So I don't even have to predict the future to say that. I think that apart from that, well, there's so many things. I think that quantum simulators, I think the neutral atoms as quantum simulators, again, have already had an impact. We have been able to learn things with collections of neutral atoms in an optical lattice that were only known at essentially the same time with the most sophisticated calculational techniques available. And I think that we're in a stage now where we're starting to learn things that really aren't able to be calculated at all. This is the essence of quantum simulation, that you use a quantum system to mimic the behavior of a Hamiltonian that you cannot solve using standard computational techniques. And I think we're just about there where we can learn things. So for example, one of the things that I think is a great example is something that is due to the genius of Debbie Jin. Debbie took the whole idea of quantum degenerate gases, which were done with Bose-Einstein condensation, using what we now call bosons, after Bose's invention of this new way of counting that, you know, I suppose most of your audience knows there's another kind of thing that we call fermions, and electrons are fermions. And as a result, they're really important because almost everything that we experience in daily life has to do with the way in which electrons behave. And what Debbie did was do for fermions what had been done for bosons. She started working with Eric Cornell, who's one of the pioneers of Bose-Einstein condensation, got a Nobel Prize for that, and thought, okay, this is great doing this with bosons. Let's do it with fermions. And she was, without a question, the premier person who made that field of study what it is today. She was the first one to get a degenerate Fermi gas, which behaves so differently from a degenerate Bose gas. And by degenerate, I mean that the particles are closer together than their quantum mechanical de Broglie wavelength. So she then did what I think was one of the most remarkable experiments, showed how you could take this gas and by manipulating a parameter that she could manipulate that you can't do with ordinary materials, basically the strength of the interaction between the strength and the sign of the interaction between the particles. She could go from something that looked like a Bose-Einstein condensation of molecules, these fermions bound together so that when you get two fermions together, they act like a boson, or something that looked like a superconductor, where you have disconnected pairs of atoms that somehow are correlated in this amazing way that produces superconductivity and produces superfluidity in things like liquid helium-3. She was able to take the same gas and tune it from one of those extremes to the other and show that nothing abrupt happened, that it went from being a quantum degenerate Bose gas to being a quantum degenerate Fermi gas without anything in the way of a phase transition happening. And people have been arguing about that for years. So that was just a really remarkable thing that I see as being a kind of a milestone in quantum simulation. Not everybody will see it that way because it wasn't that people couldn't calculate that, but it wasn't clear that people were doing the right calculation. So I think that what she did was amazing and game changing. So that's the kind of thing that I'm looking forward to in the very near future.
Great.
This is really inspiring for all young scientists that we have in our audience. Raj?
Yes, and also Bill, you're among the many things that you're famous for. One of the things that you're infamous for is asking a lot of questions.
Yes.
When we had the previous call, we briefly discussed about how you have always asked questions and how my father had taught me very early on that any statement, any sentence that is started with a question, so what, why, how, when, where, which, it will lead you to all the answers in the universe. And can you elaborate more on the significance of asking questions? Because sometimes people are afraid to ask questions.
And the art of asking good questions too.
Well, asking good questions is harder, of course, than just asking questions. But part of my success in asking questions is that I ask so many questions that some of them are bound to be good. if only by accident. I think that a lot of times I ask questions that are, from my point of view, relatively simple. And sometimes they reveal things that aren't so simple. So I ask a lot of questions. I mean, probably my infamy comes from the way in which I ask questions at conferences, and also at colloquia or symposia. And so what's my secret? I would say there's two things. One is I take notes. I know a lot of people have mixed feelings about whether you should take notes. There's been some research done, not with professional scientists, but with undergraduates, that found that undergraduates who took notes actually retained less of what was in the lecture than people who didn't take notes. And I can see that, because you have to pay attention to what you're writing as opposed to what you're hearing, and you may lose the train of thought sometimes. But for me, I find that taking notes does two things for me. One is it keeps me focused, because if I'm writing down what's being said, then I have to really pay attention to what is being said. But more importantly, for this question, whenever something doesn't make sense to me, then I make a notation that I've got a question about that. And by the end of the talk, if I hadn't written it down, I would have forgotten about that because of all the other things, interesting things that had come up in the talk. But now I've got a record on paper, because I'm taking notes, with a pen on a book, in a book that's got bound paper pages. I know that other people have more modern ways of doing this, but I'm still using paper. I just look back and I see what were the questions. And then when the question period comes in, I ask myself, which is the question I most want answered? and so I can see among all the questions that I had, which one do I most want answered? And sometimes it's a question that just has to do with the fact that there were things about this talk that I didn't understand, that probably if I had been more expert in the subject, I would have understood, but I didn't, and I wanted to. So it asked that question. So that's the other part. I have no shame about asking simple questions that simply reveal that I'm uneducated about this particular subject. Now, one of the stories I tell young people, especially about that feature, is you should always ask the questions that are simply because you didn't understand something about, the background of this. Don't worry about revealing that you're ignorant, because probably, if you think about the audience, probably 50% of the people in the audience had the same question and are so happy that you asked it because they didn't understand it either. And the other half of the audience understood things so little that they couldn't have even formulated that question. So they're happy because you've revealed something about the talk that they hadn't understood. So, and it happens to me repeatedly that people come up to me during a conference or after a talk and say, "I'm so glad you asked that question because I wasn't understanding what was going on, and your question made it more clear." And so that happens all the time for me. So I think that that people shouldn't be worried about asking what might be perceived to be ignorant questions.
So, Bill, if you have the whole world in front of you listening to you, and the world has got many problems and the people have many questions, what will be the question that you will ask the world? Imagine that the whole world is in front of you. What are the big questions that you will ask the world and the world should be asking and thinking about?
Well, of course, this has nothing to do with my career or the things we've been talking about, but I would ask the world, why don't you take climate change seriously? We are in deep trouble, and you are not doing what needs to be done about it. And you haven't been doing what needs to be done about it for the last several decades. And now, for some things, it's already too late. How much longer are you going to wait?
Well, that is a great question. And I think that many people around the world, from young as well as to the leading and powerful people, they have to answer that questions pretty fast. And that is a great question indeed. And speaking of questions, I briefly told my father that I'd shared with you the questions that he had taught me. And you said that my father is a wise man to have taught me those questions. And my father's response was, the universe is a big puzzle waiting for us to solve its mysteries by asking more questions. So Bill, keep asking questions. And many people in our audience, they will have even more questions once they listen to this lecture. And therefore, we would love you to come back and answer 1,000 more questions from thousands of people from hundreds of countries. And with that, I would let both Malu and Prachi thank you and conclude you. And from my part, we will be together again, asking a lot of fun questions and playing with a lot of interesting subjects, ideas, etc. Because the world needs more playful and curious people. And it is good to have found you.
It's been a pleasure. I'll be happy to come back and do this again sometime.
This was wonderful. Thank you very much, Bill.
You're welcome.
Wonderful. So we will all stay on the line for a few more minutes, but for our audience on YouTube, thank you again for joining us, posting your questions on Discord, and we will see you as we continue the Womanium Quantum program. Thank you.
Yes, for all our audience on YouTube, we are going to stop streaming. So thank you for joining us. We hope that you enjoyed the stories, the inspirational anecdotes, but also the scientific principles and the curiosity behind those scientific principles that Bill was able to share today. And we hope that you take some of those inspiration and keep on asking questions. And from those questions, you keep on doing experiments. And hopefully you will also get to enjoy the type of excitement and even surprises that Bill has been able to enjoy in his life, and then come back to us and share with the rest of the world those curiosities, those journeys, and those surprises and wonders. So thank you to all.